Good day, I'm Amiko Cowder with NASA Public Affairs. Mars is a fascinating planet, and NASA's journey to Mars has many challenges and many possibilities. We recently talked with NASA Planetary Director Jim Green and NASA astronaut Stan Love about taking a trip to Mars and what it will take to get us there. Here's more of what we learned about a future trek to the Red Planet in this special edition of 30 Minutes to Mars. We get an example of robots and humans working every day as it is now on the International Space Station. So for you, Stan, you can better explain some of that work and also what it's like to be living with other human beings. I don't know, what is the size of the crew? Have they even discussed what that might be for Mars?
They have discussed, of course, the engineers, the ideal number of human crew members as far as the engineers are concerned is 0, because it makes the ship so much simpler and lighter if you don't send any people. Realistically, you don't want to send too few people to be locked together in a minivan for 3 years because the social interactions can be bad. So you need a certain size of crew, maybe about 6 or so, to keep a social atmosphere that's not going to disintegrate. There's also reason to send more people because the trip to Mars is going to be expensive. We're probably going to have to cooperate with other nations and other agencies to do it, and they are going to be unwilling to pony up the money if their person doesn't get to go. So for international cooperation purposes, a crew of 4 to 6 is probably about right. If you go back and look at the history books and see what happened when we were exploring the Arctic and Antarctic around the turn of the last century, around 1900, there are cases where very small parties went for very long times in very harsh conditions and did okay. So I don't think that's a tall tent pole. Now, working with robots, on the International Space Station, we talk a lot about the robot arm, but that is not much of a robot. It's a manipulator system. The crew commands it, and it goes exactly where they tell it to. And there's a great deal more typing than there is hand controller work, but that's how you control it. The robots that we're talking about for planetary exploration are smart. They can roll forward, detect a rock, and go around the rock. Our robot arm on space station, the only thing that prevents it from hitting the space station is the crew. It has no intelligence whatsoever. So when we talk about robotic assistance on the surface of Mars, we're talking about something far more sophisticated than the jointed manipulator systems that we're using on the space station. These things will be able to follow a human along, carry tools, analyze things, be sending back telemetry to the base all the time, and they'll be able to make some of their own decisions, which is not something we see on the space station.
Yeah.
One of the, it's actually a lander that we're building right now is called InSight.
Okay.
And it's going to land not very far actually from where Curiosity is, approximately in the same longitude, but several degrees in latitude higher. And it's designed to make seismic measurements. It's going to put a seismometer down on the surface. It's going to drill several meters below the ground and then look for the heat flow. And that's all about determining how active the planet really is. Does it have a molten core? How geologically active in terms of Mars quakes, if you will. We also want to know that. Now, we know Mars is hit by meteors that are coming primarily from the asteroid belt, which exists between Mars and Jupiter. And as those impacts occur, they're going to generate sound waves, and then InSight, sitting on the surface, its seismometer will see those and then understand a lot more about the structure, the interior structure of that planet. From a scientific point of view, that's tremendously exciting because it gives us an idea of another terrestrial planet and how it's put together and tells us about the early origin of our terrestrial planets here in the solar system. From human exploration perspective, knowing how active Mars is will allow them to work in the field without getting knocked down if there are large Mars quakes. And indeed, we just don't know how active Mars is, and that will be important to know. So Phobos and Deimos, you know, some people call those the space station of Mars. You know, because you know, there might be an element of that where we go visit Phobos and Deimos first, before we get down on the surface.
Yeah. So
what are your thoughts on that?
Yeah, many of the technical problems for getting to Mars are landing on Mars and then launching again off of Mars. Mars is a planet. it's hard to launch off of Mars. When we launch people off of the Earth, we go down to Kennedy Space Center in Florida, and there are 10,000 incredibly dedicated people who put those spacecraft together, get them out on the pad, make sure everything is perfect before we launch them. And when you go to Mars and it's time to come home, you will do all that work yourself. No dedicated army of people. You will check out all the systems. You will make sure the spacecraft is fueled and ready to go. And that's a job we've never had crews do all by themselves before. So that's going to be a new one for us. Phobos and Deimos, Mars's two small moons. The larger is maybe 20 miles across, and the smaller is maybe 12 miles across. They are much easier to get to than the surface because you don't have to go down in that gravity well and then slow down and stop. You can stay higher in orbit, and the job of slowing down and stopping is much easier. And then launching off of Phobos and Deimos, you could do with a good jump. So you don't have to have big, powerful rockets and punch through all that atmosphere and get your 5 kilometers per second of escape velocity. That said, they are not easy objects to work with. So first of all, they're so small that their gravity is, every 100 pounds of weight you have on Earth gets you 1 ounce on Phobos and 1/2 an ounce on Deimos. And when we practice our spacewalks underwater in the neutral buoyancy lab, and our 150 or 200 pounds of person plus 350 pounds of spacesuit, a perfect way out in the NBL is plus or minus 1 pound, and that feels just like being in weightlessness. Your way out on Phobos and Deimos will be 1 ounce or so. So it's a better simulation of zero gravity than the simulations we use to train for zero gravity. So essentially you're on a natural object covered with rocks and dirt and dust that has no gravity. Every time you touch it, stuff is going to float away. If you just touch that with your finger, off you go. And it could be hours before you fall back down again. You will not walk on Phobos and Deimos. Your legs are much too clumsy and strong. You will barely touch Phobos or Deimos, and then you'll go drifting off to the side, and it may be 10 or 20 minutes before you can touch Phobos or Deimos again. So we don't know how to operate in that environment yet. Our weightless environment that we practice in Earth orbit, the International Space Station, is covered with handrails. And if there's no handrails, we don't go there because we need something to hold on to. Phobos and Deimos is just rocks and dust. If you feel yourself drifting away, you grab a rock, and the rock comes with you and drifts away. Whereas on space station, if we're moving away, we just grab the handrail and pull ourselves back in.
So what are we going to do? How are we going to learn how to do that?
Good question. We're working on it right now. So one thing you can do, if you can figure out how to fire a harpoon into that dusty, rocky surface, not a guarantee that it'll work. You could stretch out ropes and crawl around on the ropes. We're not sure about that. We've looked at techniques for smaller asteroids where you just take the whole asteroid and put it in a fishing net and crawl around on the fishing net. Phobos and Deimos are too big for that. You could carry a little jetpack to push yourself back, but then the fuel requirements get pretty big after you've used it a few times. You know, we have a tiny little jetpack that we carry for self-rescue on the International Space Station. We would run that out of gas in probably 5 minutes of work on Phobos or Deimos, so we need something a little more capable. So you save the problems of having to land on Mars and take off again, but you've signed up for a whole other pile of interesting technical problems that you have to solve.
Sure. And so are we talking to one another? I mean, are we gathering the information that you guys are discovering so that we understand better what we need to know in order to live off the land and get there and leave and survive and that sort of thing? How are we
I think
doing
that conversation has always been there at some level, but it's now, I think, well on its way to increasing rapidly. We now have the capability to really find landing sites of significance, both for science, but certainly human exploration. And we need to probe that. We need to really work more closely together. I think as we get down to the latter part of this decade, we're actually using this ISRU that is on Mars 2020.
Now, when you say ISRU, that's in situ resources utilization, fancy word for living off the land, essentially, correct?
Correct, yeah. And it takes in the atmosphere and creates the O2, separates the carbon from carbon dioxide, leaving the oxygen.
Okay.
And so that's an important process. And this is really that first demonstration. I think we're going to see more of those experiments as part of the scientific payloads that we do, particularly in the 2020s. So I think it's an exciting era. Mars we should not be afraid of. It's a fabulous destination for us to explore. It has so many scientific questions that we could answer, and it might actually be the first place where we find life beyond the atmosphere of our own Earth. And if we can do that, that is really a tremendous step forward in understanding life in our own universe and how it is created.
Sure. And are you ready to go?
Oh, yes. Sign me up. Although my wife might have something to say about it. But
it's a long trip.
It is a very long trip.
Yes.
And you will not be digging your toes in the sand when you get there. Okay.
So, well, and you mentioned something about some of the technologies and saying, well, we're working on this or that, but we're not quite sure. Is there going to be a way that we can be totally sure before we go, or do we just go and just kind of hope that it's going to work?
It's going to be between those. Everything in life has risk.
Right.
Flying to Mars is going to have risk. If we wait until there is no more risk, we will be landing on someone else's city on Mars because the first humans to go to Mars will be taking some risks. So we're doing quite a bit now, actually, in many different fields, medical, engineering, social sciences, to understand what we have to send people to Mars.
So, Jim, you have convinced me that this is a fabulous place. You've convinced me it's not really the place to go vacationing at. But personally, can you tell me why? Why would you say, yes, I'm ready, sign me up?
It's a place that people have never been before. And this has been important in the whole history of our species on Earth. When new lands become available, we like to go and see, and we like to go and see it with our own eyes. We as a species are curious. We want to know what's there, and we want to see it with our own eyes. And Mars is sort of the ultimate expression of that. A place
and
where
isn't
you
it
could
true,
go.
though, also, I know that our trip to the moon, they were the moon boons, right? We have lots of benefits that actually benefited all of mankind, just getting us to the moon. So do you think that we're going to get the same kind of benefits or even more going to Mars?
Well, as you develop the technologies necessary to do this kind of exploration, there's all sorts of benefits that come from that. I mean, we really, I think, helped herald in the computer age that we have now. You may not recognize it, but in the last 50 or 60 years, our knowledge of our solar system has just exploded. In the 60s, planetary scientists, when they looked at the moon, thought that the craters were generated from volcanic processes. We now know that those are impact craters. There's hardly any volcanic craters on the moon. And so our whole idea of what our neighborhood is like, our whole idea of living in this solar system, we recognize that the planet is a fragile place to live. And if we are going to survive as a human species, and a number of astronauts have even said this, we must trek out. And I think that's absolutely the right thing to do.
Can you tell me a little more about, we kind of touched base some of what we know and what we've discovered on Mars, but talk to me some about the landscape of Mars.
Well, the landscape is tremendous in terms of its variations. Huge shield volcanoes, and there are quite a few of them on the surface of Mars that have been built up over time. It would be an enormous amount of effort to be able to scale one, even for humans, and reach the caldera area. The valleys are absolutely enormous. They're tremendously deep, and they're very long. Some of the tributaries of Valles Marineris are about the size of our own Grand Canyon, which we all dearly love and are always in awe every time we see them. The other landscapes in terms of the craters and the variations that are seen are also quite spectacular. You know, where Curiosity is sitting is in an ancient river or lake bed. We see the rounded pebbles. We look and we can see regions like that look familiar to us, but yet strangely different.
And what is rounded pebbles? What does that mean?
Well, the rounded pebbles, you know, you start with a rock that's been broken away and it's got sharp edges, and as it rolls down the hill and then is moved in water and continually is rounded, that's done by an aqueous process. And so then they accumulate well downstream and create a conglomerate, and they look just like the ancient riverbeds that we have here on Earth. We can see those similarities even on Mars. So there'll be some things like that that'll look very familiar but yet different. We'll understand the commonality in the geological processes, but then there'll be things that will surprise us for sure.
And so we're talking about the geology part or aspect of Mars. Do we know much about the climate of Mars?
Well, we actually have developed global climate models right now. We're probably at the stage that NOAA, the National Oceanic and Atmospheric Administration that runs the weather systems and weather satellites and predicts our weather and climate, where they were probably in the 60s. And so we know what the wind patterns are, and we have a fair amount of information about levitating dust and transport of dust, because as I mentioned, Mars is a very dusty environment. The global wind patterns are actually fairly simple. If clouds were to form, they would change rapidly. You'd have variations in temperatures, and we could model all that, and that's really pretty exciting. Our knowledge of Mars has grown so extensively that those models will be important when humans arrive and want to know how the weather will change over time.
Yeah, it's very interesting. And so we have seasons.
Mars does have seasons. Yeah, it does. In fact, in the polar region, we put a spacecraft down on the ground called Phoenix. Now, it wasn't a rover. It was designed to be able to get under the surface and look for the water layer that we felt was pretty close to the surface. And indeed, it wasn't very far underneath the soil that we actually found that water layer and tasted it. We knew it was water. 99% pure water is what Phoenix saw. But it only lasted 3 or 4 months. The snows came, it snowed. There was so much snow at Phoenix that it piled up on its solar panels and broke them off. And so we see from orbit, as we've gone over Phoenix now during the summertime period, where the polar cap has receded, the busted up spacecraft that was underneath the snows that occurred. So we're going to see some familiar things like that, the seasons and the precipitation that does occur.
It's fascinating. Very fascinating. I see why you're signed up now.
Yeah,
I'm ready to go too.
It's an interesting place. And also, given our other possibilities in the inner solar system, Mars is a picnic.
Yeah.
Mercury goes from roasting hot to freezing cold, far hotter and far colder than Mars can ever be. Venus is hot enough to melt lead. Our own moon goes from plus 200 to minus 100 over the course of its 2-week day-night cycle, or 2 weeks a day, 2 weeks a night. Mars has a day and a night that's like the Earth, about 24 hours to go around to spin once. It has seasons. Its axial tilt, the way the sun changes its height through summer and winter, is the same on Mars as it is on Earth. So it really is the garden spot of the inner solar system, except for the Earth, of course.
The garden spot. So we've heard from a planetary perspective the things that you have hoped to discover and learn further. Once we get to Mars, are there any other things that you, as an actual explorer, would hope to learn and find when you get there?
Well, from the exploration standpoint, the important thing would be to get there, to survive and thrive there, and to come home safely. Mm-hmm. So that's the purpose of the journey from the exploration standpoint. Now, the mission that we take to Mars when the first people go is going to be not just flags and footprints like we did with Apollo. Remember, we have put 12 people on the surface of the moon, of whom one was a geologist, and that was on the last Apollo flight that ever went. The first crew on Mars is probably going to be half geologists. So that mission and its objectives will be to explore the area geologically, to collect the best samples, to do the best science, to work with a team of scientists back on Earth to make sure that they've surveyed the whole area and found as many interesting things as they can. And even among the section of the crew that's not geologists, the pilots, the engineers, they're going to have ingrained in their mind that mission success for this flight is to do good geology. Sure. So they'll have geology training. They'll be, once the spacecraft is down, the systems are safed, and we're in sort of a housekeeping mode. Those non-geologists will have had some basic geology training, and their job will be to help the geologists do the best possible science that we can on the surface of this planet and learn as much as we can. So the normal things that we think of when we're just doing an exploration expedition to get out and get back are going to be tightly interwoven with the science goals of this mission. It's going to be a very different thing than Apollo, or maybe similar to the last Apollo flight, where we did have a real geologist on the moon. And he was just in heaven because it was such a cool spot. And Mars would be even more interesting. Many more similarities with Earth, and much easier for an Earth geologist to recognize things similar to, but not identical to, things on Earth, whereas the moon is dominated by processes that we barely see on the Earth, and it's tough to sort of get a grip on.
Yeah.
Mars is going to be closer.
And with the geology being such an important focus in our initial flights to Mars, have we started learning or practicing any of the techniques, or trying to develop any of the tools at which we would actually core and get samples?
We have been running model planetary exploration expeditions out in the desert of Arizona, sometimes with spacesuits, sometimes with just spacesuit mock-ups. We do mock space expeditions underwater off the coast of Florida, where we're working mostly on asteroid techniques, because with being underwater you can be weightless, but those techniques would work equally well for Phobos and Deimos. Anything we're doing for asteroids is great for Phobos and Deimos. Those two moons may actually be asteroids that Mars captured into orbit around itself. So that kind of work is going on, but it's at a sort of a conceptual level, and we won't be able to design the real tools until we get closer to flight. One other thing to bear in mind is that the quality of our analytical equipment, you take a rock and you put it in this machine and it tells you what the rock's made out of, okay? Those are getting better all the time. Something that would have filled this building in the 1960s, you can now carry in your hand.
Yes, like our computers.
Okay? So in 2035, are you going to want this clunky thing that fits in your hand, or are you just going to hold your iPhone up to the rock and it tells you what it's made out of? So in that sense, you don't want to design the tools yet, because when you get ready to go, you want the latest technology, not the very latest, because you want something that's proven itself reliable. Because if you get the latest thing with bells and whistles, you get off to Mars and it turns out it doesn't work, it's not so good.
The glitches.
That actually brings up another point that Jim mentioned, the moon rocks and the sample return. Bringing back the samples from Mars is valuable, not just because you can't take the best equipment to Mars and measure things there, but when you have a sample on the ground, you have it for the future. So the moon rocks that we have now, that we collected in the late 60s and early 70s, are stored, they're safe, we have them. The instruments that we have today that were not even imaginable in the 1960s and early 70s, we can take that rock and we can put that in that machine. 100 years from now, when we have even better machines, we can take that rock, we can put it in that machine. So that's the real the thing that makes this return sample absolutely treasure, is that we have it for the future. You don't just have it for the instruments that you managed to send there, which are going to be old and clunky in 100 years. When we have these amazing things we can barely even dream of today, we'll be able to have those samples and analyze them using those amazing new tools as we get them.
Yeah, and talking about coring, do we know, also going back to the geology, is the composition of Mars, is it anything like Earth? I mean, are we going to get there and think, oh my gosh, this is much harder, and we're not able to do this?
Well,
or how do we know?
The rocks will have various densities associated with them. And on the 2020, we're already developing a drill concept. So we're going to core rocks. We're going to get in several inches. It'll be like a piece of chalk. Then we want to get in the hole and we want to interrogate it. We'll zap it with laser and we'll vaporize the rock, and then we'll look at the spectrum, and then we'll figure out, hey, that's a sample we want to keep or we want to move on. We'll have very high resolution microscopes, if you will, to look at the mineralogy. to see if these rocks have been, sediment has come into them because of water has deposited them. In other words, are they veiny? You know, what kind of materials there are. So that's the kind of sites that we want to go to. We'll see variations in how hard these rocks are. And we want to store those at all levels. And as Stan said quite eloquently, these are samples that will keep giving science as we bring them back to Earth and then study them, because our tools will only get better in terms of analyzing them.
It's totally fascinating, and I think that's about all the time that we have, but I really appreciate you guys coming out and talking with us. You can get more information going to the website at www.nasa.gov, and as always, continue and join the conversation on Twitter using the hashtag Journey to Mars. I appreciate you guys coming out. Thanks very much.
Oh, my pleasure.
You're
Thank
very
you for
welcome.
having me.